¿Recordaré ahora? Tengo que recordar dónde.
No te preocupes, sí, sí, sí.
Muchísimo.
Mal tiempo.
Sí, sí, sí.
Dos años, bueno.
Sí, sí. Recuerdo dónde.
Hi everyone, thank you for coming. Today the institute is a bit empty. It's not useful, but fortunately we have a few attendants today. Again, thank you for coming. Today we have Divakara. I'm going to make a quick revision of his career to give you some information about him. He made his PhD in 1993 in the Indian Institute of Science in Bangalore, India. And in 1994, he got his first postdoctoral position in the Tata Institute of Fundamental Research. And in 1996, he went to Mexico, and he now is Mexican, and that he got the Guillermo Aro Fellow at the INAOE. INAOE means Instituto Nacional de Astrofísica Óptica y Electrónica en Puebla, bueno, particularmente en Cholula. Sorry, but I cannot make a CV in business languages. And from 1997, he started to work as a researcher in the INAOE, and he has accumulated about 30 years of experience in scientific research and postgraduate teaching, and he is an expert in the star formation history or star formation rate in galaxies, mainly focusing the local universe. So,
Thank you, Jairo. Jairo was at INAOE for a few years, working with me as postdoc. So I know him. Thanks for the invitation here and giving this opportunity to share some of my recent results. So what I'm going to speak today is on these two galaxies, but focused on the topic of feedback. The feedback in the last decade or so is gaining a lot of popularity, maybe because of its possible role in quenching of high redshift galaxies, no, in the previous, early in the universe. But to understand how feedback works, we have to study nearby galaxies. So, and the James Webb is now in the last 2 years that data are available. He's making very good contributions in this field. So I will try to illustrate with these two galaxies on which I've been working for the last year or so. M82 is a famous starburst galaxies. It presents us an edge-on view. So here we can see the effects of feedback like in the vertical directions, no, filaments popping out of the disk towards the halo. Whereas the second example is NGC628. So this is a face-on galaxy almost. So where this image, both images here in the red part and there, most of the structure that you see are in the pH molecules. So that one at 7.7 micron. So in the pH molecules, you see basically bubbles in this image. So you can see many of them. So we have studied this largest bubble, and I will talk about that and the more recent work that we are doing in that galaxy. You can stop me whenever you want. Okay. So, this work that we did on this galaxy recently got accepted. That is a work with a large collaboration led by Alberto Volato in the University of Maryland. And that project is basically to observe these two classical starburst galaxies, M82 and NGC628, with the James Webb Space Telescope. So this, when the paper got accepted, this picture from the paper was published as an astronomy picture of the day, which I'm here presenting. So the portion that we analyzed is basically the central part of M82, around 400 parsec, around a kiloparsec by kiloparsec region basically. So, and in that region we see a lot of filaments, and more of that I will talk along the talk. So describe along the talk. I'll start with giving a brief introduction about the theory of the stellar feedback, and then I will illustrate these two examples. The M82 work, as I said, was done with this JWST M82 253 collaboration, and previous student of mine who is right now at Puebla University, Bolivia. And the NGC628 work was basically we have two presenting two works. One is on the characterization of the stellar populations. So where a student of mine in Mexico called Avinash is working on that along with Alexandro Bresan, and Jairo is contributing very much in the characterization of the stellar population there. And also I will briefly describe a theoretical work we did on the bubble evolution in a disk galaxy and how we can use that to characterize the disk. No, not exactly the characterizing the bubble, but we can use the bubble as some probes of the disk properties. Okay, so this the bubbles or the stellar feedback is basically because of stellar winds and multiple supernova explosions. Typical star cluster in star forming region may contain hundreds of massive stars, and all of them will go off at the same time, almost. So that creates a lot of energy and momentum in a small volume, and the pressure generated by that will make the bubble, or create a bubble first, and the bubble will start expanding. So this scenario has been proposed long back by Tenerio Tagle, who is at our institute, and Bodenhammer way back in 1988. So we have illustrated that the size of the bubble, you don't worry about different lines, but in general, for any of these models, size of the bubble grows as a function of age. So for around 30-40 million years, you easily get like bubbles of sizes of 1 kiloparsec radius, huge bubbles. So which this study illustrated that stellar populations can generate large-scale outflows. Although star clusters are few parsecs in size, but they can influence the galaxy at distances more than 1 kiloparsec. So, however, the disk is thin. This may be 100 or 200 parsecs of gas scale height. So, if you grow a shell of this kind of radius, obviously it won't be symmetric. It won't be spherical. So, it will open up along the halo, and it will go. The hot gas will go out towards the halo, and that is basically the reason why you see in edge-on galaxies filamentary structures pointing towards the halo, as it's well known in M82. So you see basically biconical structures. Similar, this is only one direction, so it will be in both the directions. So the observed images of M82 and other starburst galaxies agree very well with these simple numerical predictions. So that's why this is the basic idea behind creating these large-scale filamentary structures. Okay, so the image we have used is basically coming from the Cycle 1 General Observation Program 1701, leader by Bolato, and we have used basically in this study NIRCam images in 6 filters, which are written here. It's NIRCam shortwave detectors and long wave detectors. And in this, to detect all the filamentary structures, basically we have used this filter image, which captures the 3.3 micron pH features. And to subtract the continuum and get a clean pH image, so we have used 250M and 360M images also. So giving basically limiting our resolution basically to the resolution of the 360. 360 means is 3.6 micron image, so which has a PSF of 0.1 arc seconds, which corresponds to 2 parsec in M82, no? Which is at the distance of 3.6 megaparsec. So we can study the structure filaments as thin as 2 parsec, which is the first time that one can do in another galaxy. I mean, one can detect the structure as thin as 2 parsec. No? And so these are the images in the 6 filters basically. So what we did is, this is the one where we can see the filaments, but this has continuum. So we use this and that, and there is a technique to interpolate and get the continuum at this wavelength, and subtract the continuum to get only the emission features from the pH molecules. So this is the result of that. So the only the continuum image at the 3.3 micron, and after subtracting the original image with this continuum image, we can see the features clearly coming out. So a lot of structures are there, and when we superimpose this image with the other 2 continuum images, so we can appreciate the size of the galaxy, or the thickness of the galaxy, and compare it to the thickness, length, or height rather, of these filaments. No? So filaments go way up, whereas the stars, which are seen here in blue and green, so stars are all in the main plane, which is around 200 parsec, whereas these structures go as high as around half a kiloparsec in this image. So in a subsequent study, which is recently submitted, one led by Dan Fisher. So what we did was to characterize each of these filaments. So which is we see several filaments here, but roughly we can classify them into 4 groups. No? One here, one here, one here, one here. No? Same way in the bottom also, roughly there are 4 groups of filaments, and each filament, especially this is the most well-defined one. So we can measure the width, and it looks like this width, average width of this around 50 parsecs. So that way, doing for all the things, generally we have a width of the plumes around 59 parsec, and then northern side around 47 parsec on the southern side. No? So as you can see, it is not very neat work because the filaments are everywhere, and it is an edge-on galaxy, so we are seeing things projected. So it may be a conical structure, and we see them projected. So we understand that it is not an easy task to do. So just to get the parameters, so this kind of exercise tells us that so typically each plume is around 60 parsec of size, and also the most of the flux in the pH molecules is contained in these filaments. You know? Most of the flux. So diffuse emission contributes only 30% of the remaining flux. You know? So what we did was to take cuts on the northern and the southern sides. I will mostly describe the northern side, which is better defined, and to see the correspondence between the pH emission and other tracers of interstellar medium. In this case, we are plotting pH in their intensity profiles. pH is plotted in black, and the Passion alpha, which is the ionized emission, in red, and CO in green. So the CO resolution is around 1 arc second. So that's the best available for this galaxy. So whereas other emissions are 0.1 arc second. So it is a factor of 10 difference is there in the resolutions. So that's why first I'll compare with the Passion alpha, you can see that the correspondence is very good. Wherever there is a peak in pH, there is a peak also in the ionized gas. So which means that the pH and ionized gas are in the same plumes, same regions. So whereas CO, the lack of resolution does not allow us to make a firm conclusion, but in general, wherever there's a peak, there seems to be a peak also in CO. So the general picture that we think it's happening here is that all the three components, that is the molecular cool gas, the ionized gas, and the pH, which is basically dust, so are all in the same regions of this outflowing gas. In the next, I'll show the comparison with the X-ray gas. So most of the structure in that biconical structure I showed in the beginning, so that is seen in the X-rays. Most of the volume is filled with the X-rays, and here the X-ray is plotted in the blue here. So this is the bottommost, the middle one, what I showed previously, and the top one. So three sections. So the height above the plane is written here, the northern side. Other one is for the southern side. So this X-ray, basically the cone, it goes like this somewhat, as you go up. So, and it does not seem to be correlating with the pH structures. So maybe pH structures are around the cone, whereas the cone itself is basically contains X-rays. So it is because of this projection effects, we can't make really a firm conclusion, but general idea we are getting here is that pH avoids the X-ray hot gas. No, it may be in cold clumps sitting inside inside the general the cone area. No? So that is the conclusion from this. And further details we are studying here. So inside the big plume, so there are a lot of filaments. Individual filaments, what are the structures? So here again selecting where it looks beautiful or can be analyzed. So they have cometary structures. So the cometary head is pointing towards the disk. So this is the northern region, disk is in the below. So there's a bright spot and there's a tail. So that is the general structure, whereas the southern side, disk is in the top, and so it has that kind of structures. General width of around 10 parsec of individual filaments. No? So we have 2 parsecs of resolution. So they are bigger, much bigger. They're resolved structures. So they go like in bundles, and they have lengths as long as like 400, around 100, 200 parsecs in some cases. Each of these individual filaments, they break. So in all the regions we can't trace all the way 200 parsecs, but in some have this kind of sizes. So the idea of doing these things is to compare the predictions of theoretical models, where this is one of the recent theoretical simulations of this outflow. So predict a lot of substructures of parsec size. So here from the center you have the conical structures, and you can see a lot of density. It's density basically clumps of high density, and the sizes of these predicted sizes compare very well with the sizes that we see, and the cometary structures also. Some of those features have these cometary structures. So, but here we know exactly how these cometary structures are formed, and in these models, what they call as the cloud crushing models. So when the hot gas goes out of the disk into the halo, so it carries with that some of the molecular clouds. So these molecular clouds are floating there, and they won't survive because the hot X-ray gas will start destroying the cloud. And for the calculations, the destroying time or cloud crushing time scale is, it can be as long as 3 million years because of their models. So whereas the time to move a typical cloud to 200 parsec height can be less than that. So it looks like clouds survive up to 200 or even more parsecs before getting crushed by the hot gas. So that's how they are able to produce. And so it looks like we are seeing such structures in M82. No? So for the first time, so these kind of details of the emission have been they have been able to study thanks to the JWST resolutions. No? So this, as I said earlier, these are pH molecules, so they are like dust particles. So that so they cannot be there in the halo. No? So the idea is that they are pushed from the disk along with molecular clouds, and as the clouds get destroyed, these pH features appear there. No? So they won't stay as pH for much long time. So you need to have this continuous outflow of material from the disk towards the halo. So that is the general ideas from these structures. So now I'll talk about another interesting idea is to look for clusters associated to these plumes. Plumes require a lot of supernovas. So supernovas are high mass stars basically, but the other low mass stars will be still there in the clusters. So we can try to look for association at the base of these plumes so that there are clusters. That was the idea, but till now I've been trying to look for that. It is not that easy. So what we have done so far is to identify all the clusters in these James Webb images. And back in 2008, we had cataloged clusters on HST images in this galaxy. So we are basically comparing how many new clusters are there in this central region compared to the clusters on the HST images, which are optical images, whereas here these are infrared images. So these images penetrate the dust, so we can hope to get a lot of embedded clusters. You know? And also James Webb has much higher sensibility than HST. So what we find that the embedded clusters are not much. We have a few of them, but many of the new clusters that we find are basically very low mass clusters, and there are plenty. And here we are. We'll go to the number statistics soon. So here we are comparing in some of the region. This is the famous the nuclear region of the nucleus of the M82. The three structures that HST discovered. So these are the three. So these are the HST images, and on the James Webb image, you see that these clusters are not that easily seen like in HST. No? So a lot of extinction here. Looks like optical clusters do not somehow experience that much extinction. And so then we have additional clusters in James Webb here, which is hardly seen in the optical, and some counter examples. Curiously, also we have some very bright HST cluster it is absent here as a cluster. No? Maybe it is not because of the resolution. It is resolved in this maybe. So that's why that we are analyzing all these kind of structures. Whereas here in this image, so these two are infrared cluster which are not present in the HST images. So we are still in the process of characterizing all these clusters. So we have totally 1,348 clusters, compared to 200 clusters that was detected in the HST images in the optical bands. So what we did right now is it's a plot of all these 1,348 clusters in a color diagram where we can hope to get an estimate of age or extinction, but it turns out that the extinction we can get from these plots because this is 250 minus 300 N, 2.5 micron minus 3.6 micron, and this is 140 and 250 M, these colors. And 1 to 10 million year population is expected to have this color. Hardly it is sensitive to this color. And so in this color, because of the nebular emission, we expect 1 to 4, 1 to 6 million year age population occupy this. But what we see, all the observed points are here. So that is consistent with the different regions having different extinctions between around 3 magnitude to like 20 magnitude of extinctions, which is consistent with the earlier estimations of optical studies of the central regions of M82. There are some regions with as much as 20 or 30 magnitude extinction here. So we also characterize the mass function. So the mass function is generally consistent with the power law with an index of 2, gotten 1.9. Comparing that with my earlier study for the HST clusters, so that is this plot. So there is a scale is different, but normalize all. So the observed the slope, the power law slope is consistent with the slope we had obtained for the HST HST clusters, and in general cluster masses range between 10⁻³ to 10⁻⁶ solar masses. So that's basically where we have found most of the clusters is the low mass clusters in this 1,000 to 10,000 solar mass range. So that is the new thing from these JWST observations. Okay, to wrap this part of the work, so the James Webb observations are able to detect the plumes in pH now up to around 400 parsecs above the plane, and such plumes are seen on both the sites, and the location of the plumes agrees with the locations of fraction alpha, basically the ionized gas, and CO, and avoids the X-ray emitting regions. And these plumes have around 50 parsec of width, and inside the plumes, the filamentary structures have it's basically made up of clouds of around 10 parsec width. These observed structures agree with the recent cloud crushing simulations which predict these cometary structures, and the pH plumes are surviving parts of the clouds that are launched from the disk by the outflowing super winds, and they are not able to identify the clusters so far. No? So that's at least I hope to identify at least one of these filaments into a cluster. No? So that work is in progress. So I'll switch to the next galaxy. If you have questions, we can make a stop.
So in the extinction calculation, how did you estimate the extinction in that with the color diagram?
Yeah, basically, if for a 4 million year population, the expected color is this here. So the reddening vector is along this line. So it is for a 20 magnitude extinction. So this color this will go up to that point. So these are basically this is if there were no extinction, all would have been here. So then it is stretched out because of different regions having different extinction.
So did you done some stimulation for that?
No, basically using the extinction curve. So we used the extinction curve in the infrared, So the color excess you can be converted into extinction using extinction curve basically.
So color excess versus extinction.
Yeah, that is relatively useful. Yeah.
I have a question. It's more about M82 in general than this, but are stars being formed along the filaments that you're detecting there?
Very interesting. Yeah, I've been working on that, and yes, I see a lot of structures vertically, like alignment of stars in the new images. You can see alignment of stars along the filament, not the particular these filaments, but there are filamentary stellar structures. Different kinds.
Closer to the disk.
Yeah, closer to the disk. Not 400 parsec above, but very closer to the disk. So in all angles they are there. You can, I mean, the image is too big. When you make zoom, you can see that there are filamentary structures. So yeah, it's interesting that they're still along a line. So because in a few million years they will all disperse, but I see such structures. So exactly, my idea is that probably even in the inner halo, I mean bottom halo, stars can form in these filamentary structures.
I don't know if that case is linked or with the case of the Milky Way, when some researchers take Gaia and select some moving groups in this, and they trace a lot of kind of filaments, but these filaments are stars and nearby the stellar disk. So there is a stellar streams, but they are not from another galaxies or merging process, but they are from the internal dynamics from the disks. I don't know if they are linked, but I saw some kind of much more shorter than this scale. So.
And actually, I observed this galaxy with the UVIP. So in the UVIP images, I didn't see the star forming clumps above the disk of this galaxy, but I have seen some distortion in the left side in the UV images. Even Galaxy also has some distortion in left side.
Yeah, that is less extinction side actually. Yes. The eastern side. Yeah. If you don't have, I will go into the next galaxy, the phase 1 galaxy. So in this galaxy, since it's phase 1, we can see the structure of the bubble, no? Whereas in Edge-on, only we can see what's going out. So here, probably things are going out, but we cannot see that. So in a study that we published last year, so when the new images of James Webb came, so we got excited and okay, the prominent structure that is seen is this bubble. So we started, okay, let us start working on that. Javier was at INAOE at that time, Jairo also. So what we try to look for is on the HST images whether there is something inside. So here we don't see anything, basically. So here we can see the superposition of different filters. So in the blue we have the HST blue band, and in the green the Muse H alpha image, basically, and in the red the James Webb 2 micron image, and the contours are the contours from this image, which is 7.7 micron pH feature. So the bluer contours, whereas this green is the inner portion of this bubble, so this yellow side. So basically, this is a shell we are seeing, and the empty space or the bubble is basically inside. So we look for the stars which are inside these yellow contours, and they must be responsible for the creation of the bubble. What we did is to estimate the ages of each of these stars using the color magnitude diagrams, and so what we found is that they don't belong to a single age, so they have a distribution of age. Most of them are as old as around 50 million years, and there are some in other ages also. Only inside there are no recent star formation, all the recent star formation is in the shell. So we don't have any stars younger than around 4 million years inside the bubble. So that's why most of the stars are old, as like 50 million years, and the total mass of the stars inside the bubble around 10 to the 5 solar masses. So what surprised us is that we are expecting to find some very compact clusters because stars form in clusters, and we are expecting that they will be still in clusters. But what we found is that stars are distributed in the entire volume, which is 1 kiloparsec, this diameter. So stars are everywhere. So it seems like clusters get destroyed very soon, and they occupy the entire volume of the bubble. And also what we saw is a tendency for newer stars to be closer to the shell rather than the center. So we found the age gradient, and which suggests that the star formation has been triggered by the expanding wave. So we proposed a model where maybe the first generation of stars has created a bubble, and then that bubble got expanded, is expanding and accumulating more gas. And as the gas reaches some critical density, it will collapse and form stars, and the process goes on. So that is the scenario we suggested. And in that scenario, younger stars would be closer to the shell rather than the center. So that's what we found in this in this particular bubble. No? So this here the contours in this image are the 21 micron images as peaks in the JWST images. So these are coinciding with the H alpha peaks. So telling that they are really young star forming regions are at present at the edge of the shell. So it agrees with our scenario that the star formation is progressively moving outside. So that was the study we did. Now we extended the study to know whether that is a speciality of only this bubble, or we wanted to know how can we generalize that tendency. So now we extended the study to another 21 bubbles. So as you can see, we detected all the bubbles which are more than around 100 parsec in radius, and and also we use now James Webb photometry, stellar photometry, to obtain the ages of individual stars. So this where Hyro is also working on this characterization of these ages of the stars. And what we find is that James Webb is very good in detecting these red supergiants. Okay, most of the stars that James Webb detects are the disk stars, which are in the red giant branch, and the bubble-related stars are basically in this branch, which is the red supergiant, which occurs after around 7 million years. It can appear even at ages as this is up to around 100 million years. It will appear. Most of the red supergiants are up to around 50 million years. So we can find the ages of these stars, and from that diagram, whereas those stars which are in the main sequence are better traced in the HST images. So we are still in the process of obtaining the precise ages of all these stars. So as just the preliminary results, so showing here the star formation history that we obtained for this big bubble using only the HST data and using the James Webb data. So we see that the star formation rate, what we obtained using the earlier analysis using HST is here, and now we see that we recovered that using the James Webb data, which is which has star formation, which is slightly extended here. It goes almost up to 100 million years, but the peak is at around 50 million years. So that is for the same bubble, whereas for the other bubbles, So we see similar kinds of peaks. So in general, agreeing with the idea that the star formation is going on in the bubbles for around 50 million years. So that's the general idea we get. We are still in the process of exactly finding the ages. So, and the clusters, we don't find any compact clusters in these bubbles. They're all distributed like in the big bubble. The big bubble, by the way, is known as the phantom void by other people. So, so that is, so structures are, I mean, the distribution of stars are, the stars are distributed in the entire bubble, not just in a single location. And so in general, the star formation scenario that we proposed seems like it's working in these bubbles. I'll illustrate this one of the preliminary plots we have generated. So where we can see in the plus plot the characteristic age for each bubble is plotted against the radius of the bubble. So what we see is that if the bubble is expanding, so at 10 kilometer per second, then this is the curve that is expected in this plot. So the most of the plots, I mean, there's a clear tendency that the older bubbles are larger than compared to the younger bubbles, as expected. So, and the data are consistent with the expansion velocities of between 1 to 10 kilometers per second, which is expanding at a uniform rate. So that's why independently we are usually expansion of the bubble is inferred using radial velocity observations. So here we can infer directly using measuring the radius and the ages of the stars. And also in this plot, it is somewhat complicated. What we have plotted is the distance of the blue stars from the center of the bubble, normalized to the bubble radius. So whereas other stars are shown in the red, and the blue stars here basically, the blue points are basically the location of the bluer stars in the bubble. So most of the blue, except a few exceptions, bluer objects are outside compared to redder objects, which is indicating that bluer stars are closer to the shell rather than the ring. And in this plot, what we measure, that is to illustrate that the clusters are stars are not confined to clusters. Instead, they are distributed everywhere. So we found the clustering length, that is the radius that contains like 15 stars. That's the kind of measure we obtained. So 15 stars are contained in radius of like 100 to 350 parsec, which means if they are all clustered, they should be like less than 10 parsec, but the typical sizes increases with the bubble size. Bigger the bubble, larger is the volume that stars occupy basically. So that is for the young stars. So if you older stars occupy, that is for the old stars basically, older than 20 million years. So they are distributed everywhere. So that is the, which is all consistent with the results that we have inferred for this phantom void. So just to finalize, another interesting theoretical work that Santiago Jimenez carried out basically during, he was a PhD student at INAOE, so now he's at Prague. So what he did is to reproduce numerically this phantom void. So this is from a 3D simulations and trying to reproduce exact shape that is observed, and also exact shape in the column density of the gas. Most of the gas is either in neutral, either in atomic or molecular form, the sum of this is what we observed is this. What we observed is this points, blue points, and this black line is the model, the three-dimensional model. And in this model, basically, you have a uniform distribution of gas to begin with at some density n0, and then you explore the supernovae, and the gas gets pushed, gets piled up, and so you get bubbles. And with the time, I'll come back. So with the time, here it is a 10 million year, 15 million year, and for example 35 million year. So it is a 3D model. So given a scale height, so it won't be spherical. So immediately it will stretch along the halo, and as the time goes, so it will stretch more and more towards the halo. No? So that is how. So that is the edge-on view. Whereas if you see the face-on view, so the density distribution at different epochs will be like this. No? So the bubble radius grows with the time. So and the location of the peak after any given age depends critically on the density that we choose. So because for the given amount of energy from the stars, so if it is dense, it won't move faster. So it will be slow, the radius will be smaller. Whereas the density is low, it will grow much faster at a larger radius. So that's why the observed location, if you know the age of the cluster, age of the stars, so then the position or the radius rather depends on the density of the interstellar medium. So that's why we can use these bubbles to measure the density of the mid-planar disk, which is hard to measure. So there is use of these bubbles, no, to understand the galaxies. Also, the level at which gas density is there at the center of the bubble, so that depends on the halo density. Basically, because we are projecting, so in the basically in this direction, so we are projecting like this. So if the halo density is larger, so it will have a larger value, and vice versa. So here we have plotting for different halo densities. So where what will be the central surface density? So that's why we can really obtain this parameter by comparing with the observations. You know? So only unfortunately for this phantom void, so we had only upper limits on the gas densities, so we couldn't exactly conclude, but the best fit values are written here. You know? So it's around 2.2 atoms per centimeter cube is the central density, with the scale height of the gas that required to produce this is around 220 parsec, and the stellar density in the disk is around 30 solar mass per parsec square, and the shape depends very much on the rotation curve. This is elliptical because the shear produced by the rotation is responsible for this the ellipticity. So that we use the observed velocity of 165 km per second for the rotation curve, and so we give density for the halo of 0.05 particles per centimeter cube, and stellar scale height of around 400 parsec. So that is that was interesting that we can obtain physical parameters using the bubble here. So I think with that I stop. Basically, what I tried to summarize is the structures of these feedback-related structures in M82, which presents as a edge-on view, so we can see the plumes towards the halo, whereas in the face-on galaxies we can see the bubbles, and then NGC628 there are more than 20 bubbles of radius more than 100 parsec, and the stellar population responsible for a bubble are not in bound clusters, they are distributed. So if they are formed in clusters, in 50 million years, they are all destroyed and they're dispersed, the stars are dispersed. And in the last point, so the gas density profiles of bubbles can be used to obtain disk and halo gas densities, using the simulated results. So thank you for the attention.
Okay. I suppose we have some questions. So we observed a lot of contents here today. So
I think it would be worth to look at even smaller and younger bubbles to try to find the progenitor clusters.
Exactly. Next, we are going to do. Yeah. We are trying to. I mean, that are new and techniques we are developing. So exactly. So the resolution and number of stars will be less there. Crowding will be. So we will do that, but we started with the easier problems.
Right.
So exactly, that's what there we may be able to. I mean, there are a lot of interesting things. We will be able to tell exactly when the clusters get dispersed, for example. So that's the idea. Thank you.
A very nice one. So do you have any plan to compare with the H alpha star forming region with the UV inside the bubble? Because there is one, again, UV data for both
Yeah.
galaxies available.
Exactly.
And we already have one paper about the bubbles and the
Yeah.
star forming regions.
In NGC628.
Yes. We studied 3 galaxies. One galaxy was NGC628.
Yeah.
So, do you have plan for this comparison of the star forming regions in alpha and between inside this?
Yeah, that you mentioned, yes, I had planned, but with the JWST data coming more and more, so that is getting pushed. What we found, I checked the UV image of these bubbles. So wherever the blue stars are there, you see the UV structures. So like in the ultraviolet, it's a good filter to filter out all the background stars. So background stars you don't see. So you see only the bubble star, that is good. Only resolution we can't now detect their individual stars. So because of the resolution of 1.5 arcsecond, the UV data, so what we get is wherever there's a lot of stars together, we get some emission. Where if they're distributed, the sensibility is not enough to detect. So I mean, in one way it is nice, we can easily detect. Easily infer the presence of blue stars using ultraviolet data. So only resolution is the problem. To count stars and get the age, we have to use SSP in those studies.
Yeah, at least different age of star formation regions you can find.
Yeah, age maybe we can find. But for that galaxy, I think you have FUV also. I think
Yes.
FUV and NUV also. So.
Yes.
Yeah, that is
it
good
was
thing.
observed before 2018, so
Yeah.
we have both.
Yeah, that way that age can be found. This is that. Yeah, go ahead. Yeah.
That sounds great. That sounds very interesting to get, and you can see maybe the age of the stars changing as well.
Yeah.
Using the UV. Anyway, I was wondering about the density of the gas that you were showing in the last. So it's. I'm trying to.
You have to read it. 10 to the minus 3 particles percent. It is halo density.
Okay.
Halo
That is very low.
Yeah.
Okay.
Yeah. The particle density around few. We tried at between 1 and 10 particles per centimeter cube in the disk.
In the disk.
Yeah. It is any part of the disk, not really dense regions.
Okay. That was.
Yeah, this is a halo
I was
density.
like surprised at the number. Yeah.
Yeah, this density is between 1 and 5 particles. So, show there. But between that small 1 and 5, the radius changes very noticeably.
I'm guessing within the bubble, or at least in the edge where you can measure the H alpha, that would be much denser, no?
Yeah, exactly. Yeah, this is the pre density. Okay.
Before the-
yeah, the model assumes that there's a uniform disk, and you start an explosion there, and the gas is swept up, and it is forming new stars. You know? So it's the
Okay.
recipe for this model. Yeah.
For the M82 work, you have in the continuous subtraction, right?
Yeah.
For the pH. So for that continuum estimation, have you considered a continuum as a like constant or this considering this?
Yeah, there is the FANGS people have developed a formula to subtract the continuum, use the same strategy. So it is an iterative subtraction because the 360 filter also contains some pH. So that's why you have to first estimate the pH at 3.3 micron and scale it to subtract that pH from the continuum at 360. So like that iteratively you do. Whereas 250 is clean, it's only continuum, but 360 has some pH continuum and some nebular emission lines also there. So that's why it is done iteratively and that for every pixel. Every pixel that coefficients are found out, and that way you generate a continuum image first. So, and we see that continuum images have no pH features, which illustrates that the subtraction process is good. So that was that. So earlier, without continuum subtraction, no, without the, this is interpolated at 3.3 micron itself. So, but it uses 250 and 360. Yes. With 360, there is some filamentary features. Scaled down version of that, but some. So, but we obtained iteratively that contribution and subtracted it, and it's the pure continuation. Some structures are still seen very 1% level maybe. So, but it works very nicely. These routines.
What happened with this material? It falls again to the.
It will fall again. It will fall again probably as high velocity clouds in certain galaxy. Actually, the Guillermo Tenerotaglia's paper and all, they're motivated by the high velocity clouds. How to explain those days? That was the topic in the 80s. So, yeah, they will fall back at high velocity clouds.
Another question? Okay, let's think again. Thank you for coming.
No he podido controlarlo.
Excelente.
I couldn't help